everybody. Welcome to the third day of the workshop. We're delighted to have Tim Roughgarden from Concave University starting the day. Tim, of course, is an expert of algorithmic game theory that needs no introduction. He has done seminal work in this area and written some of the most influential textbooks. And today he'll be talking about aggregating conflicting forecasts. Thank you so much, Tim. It was yours.
All right. Thanks very much for the intro, Georges. Appreciate it. Also, thanks to all of the organizers for the invitation to speak. Very happy to be participating. And also very sorry I can't be out there in person. I know there's sort of a lot of old friends of mine I haven't seen in a while out there. So hopefully we'll get to catch up soon. In any case, what I wanted to tell you about this morning is some joint work I've been doing with my PhD student, Eric Neyman, and it's going to be called Aggregating Conflicting Forecasts. This is drawn from an EC paper from last year, as well as two papers that are under submission. I say joint work here on the slide. Honestly, that's being like way too generous to myself. What's actually been happening is sort of Eric has, almost single-handedly, like a force of nature, been developing this kind of amazing theory he likes to call algorithmic epistemology. And so this talk is basically going to be sort of curated highlights of a subset of his work. Not all of his work connects very strongly to machine learning theory, but some of it does. And that'll naturally be the part that I'm highlighting today. All right, so I know there's already been a couple talks about sort of forecast calibrations, et cetera, this week, but I really don't want to make any assumptions. So let me just start at the beginning, right? So aggregating forecasts, what does that mean? What's a forecast? Mathematically, a forecast is just a probability distribution over some space of things that could happen. Simplest possible case, which is still very interesting, is where you just have two possible outcomes. Something either happens or it doesn't. It either rains this weekend or it doesn't rain this weekend. And we're going to be interpreting these distributions as predictions, right? So a meteorologist who says a 40% chance of rain, we identify that with the distribution 0.4, 0.6. Now in machine learning, especially supervised machine learning, we think about predictions all the time, obviously. We often interpret the outputs of models as predictions in that sense. For this talk, I think it'll be extra meaningful if you also think about examples of predictions you see on the news every day. So something like the outcome of some election, or whether taking some action will lead to military escalation, for example. All right, so aggregating forecasts suggests there are multiple forecasts. So that's what I'm going to be interested in. Okay, either because there's different people using different models, or there's just different experts with different opinions. We're going to be looking at when you have multiple, generally non-agreeing predictions about the same outcome. Right, so maybe you check two different weather apps. Right, one of them says 40% chance of rain, one of them says 70% chance of rain. 538, I'm sure many of you know, sort of uses a bunch of different polls that in general are making different predictions about the election. Whenever you have, in this event, like, so if you're a decision maker and you've solicited predictions from multiple sources and you get conflicting signals, there's a question of what should you do? Is there some reason to believe one expert more than another? Is there some sensible way to interpolate or sort of aggregate the forecasts into a single one? And one seed I want to plant sort of right here on slide 1 is that sort of the right way to solve this problem, the right way to do forecast aggregation, it may well depend on aspects of the application that you're looking at. So if you're just planning your kid's birthday party this weekend, right, and one weather app says 5% chance of rain, one says 0.5% chance of rain, you kind of don't really care that there's a factor 10 difference. So you're like, whatever, I'm just going to plan the birthday party for outside. Sounds like it's going to work out. If you're talking about, estimating the probability of military escalation, the fact that, one of two military experts said 5%, even though the other one said 0.5%, right, you might interpret that information differently than you would just for planning a birthday party. Okay, so that'll show up later when we talk about the choice of a loss function. All right, so we want to aggregate forecasts. Perhaps it depends on some aspects of the setting, but in any case, we want to reason about, principled ways of doing this. And one thing a theme to look out for in this talk is we're going to be taking what I think of as a very kind of computer sciencey approach to this problem, in the sense that we're going to want to basically minimize our informational assumptions subject to having a theory that gives us interesting advice about how to do forecast aggregation. So what we will not be doing is assuming some like joint distribution over everything that is common knowledge to the decision makers and all of the experts up front. Okay, that's the thing we don't want to do. We want aggregation methods that are kind of robust, not sort of distribution free. And so for those of you familiar with the literature on prior free or prior independent auctions, which are kind of a computer sciencey alternative take that favors robustness over optimality compared to traditional auction theory, you might see some vague analogies with the stuff I'm going to talk about today. All right, so how do we aggregate? Well, so the object of study is going to be an aggregation method, which just takes as input a bunch of forecasts and spits out as output a single forecast, the aggregate. What might an aggregation method look like? Well, maybe the very first thing you'd think of is you average. If one weather app says 40% chance of rain, another one says 70% chance of rain, you say, well, I'm going to interpret that as an aggregate prediction of 55%. Okay, so that's just averaging the forecasts. This is also known as linear pooling. An obvious extension, if you have some reason to trust some experts more than others, would be to have weighted averaging. So here you associate the experts with non-negative weights summing to 1, and instead of a regular average, you take a weighted average. What else could you do? Actually, there's a lot of other things you could do. Let me mention what's probably the second most well-studied way of aggregation in this context, which is called logarithmic pooling. And basically the idea here is you take, I should have said, as far as the notation, so when you see linear pooling, P star, that's a vector indexed by outcomes, indexed by capital X. Okay, that's a probability distribution. I here refers to one of the experts. Okay, and so P sub I is the forecast of expert I. So that again is a vector indexed by capital X. All right, so logarithmic pooling here, basically you're going to do a geometric mean instead of an arithmetic mean, because you look at the products of the probabilities rather than the sum. And again, it's quite straightforward to add weights if you wanted to treat some forecasts as more important than others. Then you would just do the corresponding weighted geometric mean. Averaging and weighted averaging, I'm sure, strikes everybody as supernatural. In case logarithmic pooling strikes you as at all sort of unnatural, let me mention that there is sort of, in addition to just people who've used it, there's also work that justifies it in various ways. So there's certain Bayesian settings where it actually is sort of in some sense the right thing to do. You can also characterize logarithmic pooling as the forecast which minimizes the average KL divergence with respect to the report, with respect to the PIs, with respect to the end expert forecasts. So, I mentioned weights in passing here, like it's trivial to add them to these two specific examples. Actually, the expert weights are going to be a super important thing that we focus on for a lot of the talk. So let's go ahead and make the expert weights a first order object. So now an aggregation method is not a function just from forecasts, but from forecasts along with weights for the experts. And its job is to compile all of that information down into a single aggregate forecast. Okay, so that's what we mean by an aggregation method. We would like a theory that tells us when we might want to use one aggregation method rather than another. All right, so to have such a theory, we need some notion of like how good a forecast is. Okay, like the performance of an aggregation method as per the accuracy of its output, of its forecast. And because we're taking this sort of hardcore non-Bayesian approach, right, we don't have a prior, right, we can't really talk about the ex ante performance of a forecast. It's going to depend on which outcome is realized, whether or not it rains this weekend. So we can really only talk about sort of the ex post accuracy of any forecast, in particular of an aggregate. And so the way we're going to quantify accuracy ex post is using a loss function. Okay, so capital L takes two arguments. P here is a forecast, so P is a probability distribution over X, over outcomes. And J is a specific outcome, the outcome that was actually realized. Intuitively, right? So if you put a lot of probability on the outcome that actually happened, your loss should be small. If you put very little probability in your forecast on the outcome that actually happened, your loss should be high. You kind of screwed up, at least that's how it looks ex post. This audience, I think, will be plenty familiar with lots of different loss functions you might use. I'm going to mention two. First one, squared loss. So this basically, you just take the forecast, and you take the standard basis vector for the realized outcome, and you look at the squared Euclidean distance between the two. So that's a very sort of standard loss function. Another very standard one would be log loss. So here the loss is going to depend only on the probability you assigned to the actual realized outcome J. And it's going to be the logarithm of the reciprocal of whatever probability you assign to it. You'll notice that for the best possible scenario for you is that you predicted with 100% you predicted with 100% probability that J was going to happen, and then J did happen. In that case, you can check, you get 0 loss in each of these cases. The worst possible forecast is where you deterministically predict some outcome other than the one that actually happens. In that case, the loss, of the squared loss is going to be 2, and the log loss is actually going to be infinite. So you'll notice that, as the forecast, the probability of the realized outcome goes to 0, the log loss is blowing up to infinity, which eventually will be an interesting distinction. If you like, you can take affine transformations of these loss functions. It really doesn't change anything. For example, if you want to rescale the squared loss, feel free to do that. So we're going to want a theory that's pretty agnostic as to the loss function, that gives good advice simultaneously across lots of different loss functions you might use. The one thing I will always be assuming is that the loss function is what's known as a proper loss function, of which squared and log loss are 2 examples. What does proper mean? It just means that if there's something to learn, like the optimal strategy is to learn it. Okay, so if there actually were some true distribution from which the outcome was sampled, and again, we are not assuming that that's the case, but it's just a condition on a loss function. If it so happens there really is a distribution from which the outcome is drawn, well, the loss minimizing forecast, you would like it to be the accurate one, okay, the one from which the outcome really is being drawn. And that's the definition of a proper loss function. Okay, so the expected loss minimizing forecast is the accurate one. Any inaccurate forecast will only get you higher loss. If those of you familiar with the theory of strictly proper scoring rules, this is really the same thing, just multiplied by -1. Okay. All right. So that's sort of the basics. Hopefully you understand what I mean by the words in the title: forecasts, aggregation methods, loss functions. In this next part, I want to really kind of spell out the exact learning problem that I want to study in detail, okay, which is going to be the online learning of weights for the experts who are submitting the forecasts. Now, there's kind of a lot of parameters we've talked about thus far. In fact, there's really actually kind of 5, if you think about it. And so I want to give you a mental model of how to think about these 5 different ingredients. Right, we've got the loss function, we've got the aggregation method, we've got expert weights, we've got expert forecasts, and then we have the eventual realized outcome. Okay, so those are the 5 things. I want you to think about, like, someone chose the aggregation method chi for us in advance. Okay, so at least for now. Think that someone told us we're going to be using linear pooling, or someone told us we're going to be using logarithmic pooling. Okay, and we don't have an option to change that for the moment. We do have control over the expert weights, right? So if we have reason to believe we should pay more attention to some of the forecasts than the other, then we're free to sort of express that in weights that we're going to feed into the aggregation method. Remember, an aggregation method takes both weights and it takes the forecasts. The forecasts we're going to be thinking of as chosen by an adversary. Okay, so they can be just like whatever, we don't know. Okay, and at least initially, we're also going to give the adversary full control over the realized outcome J. Okay, toward the end of the talk, if there's time, I'll talk about a more restricted adversary in which the outcome has to be in some way related to the expert forecast that the adversary also got to choose. Okay, and so now you see, so once we have all these ingredients, we can talk about the loss of an aggregation method on a particular realized outcome, right? So the aggregation method takes as input the weights from the top, the forecast from the side. By definition, it spits out an aggregate forecast, which I'm calling P star. When the adversary picks an outcome J, we're some realized loss. Okay. So those are the 5 ingredients. Chi, think of as chosen in advance. L, think of as chosen in advance. The PIs and the J, think of as chosen by an adversary. The weights, think of as chosen by an algorithm. Okay. So with that setup, we're going to be using what I think is the sort of obvious online learning problem you might state at this point, if you're familiar with sort of just kind of typical online learning problems and regret minimization. Okay. We're going to think of the loss function and aggregation method L and chi fixed in advance, once and for all. And then things will play out over time steps, okay, where basically our learning algorithm makes a decision and then the adversary sort of chooses something, we suffer a loss and we move on, okay? Like I said, the only thing under our control is going to be the expert weights. So at time t, the learning algorithm has to choose some value for the weights, presumably based on sort of past performance of the various experts. And then the adversary chooses everything else. So the adversary gets to pick the expert forecasts, so those inputs to the aggregation method. So now that the weights have been fixed and the forecasts have been fixed, the aggregate forecast P star for time t has been forced. And then the adversary gets to pick the realized outcome. And then the learning algorithm suffers whatever loss. Okay, the loss with respect to the a priori chosen loss function capital L, the output P star of the aggregation method at this time step, given the weights that were chosen by the learning algorithm, and given the outcome J chosen at this time step by the adversary. Okay, so that's the online learning setup. And now what do we want? What makes for a good learning algorithm? Under what conditions do we say we picked the weights well? Well, obviously we'd like the total loss to be small, right? That's how we're measuring accuracy or performance. We suffer loss every time step. We'd like the sum of the losses to be as small as possible. But small relative to what? Like if the total loss is 117, is that good? Is that bad? And so as usual in online learning, we're going to take as our benchmark kind of the best fixed strategy in hindsight. So here in hindsight means all capital T time steps have elapsed. Everybody's seen the adversary's choices. Okay, so the expert forecast that it picked at each time step, the realized outcome that it picked at each time step. Given the forecasts and outcomes that the adversary chose, there will be some weight vector W, expert weight vector W, that among all weight vectors minimizes the total loss. Okay, that's going to be our benchmark, and regret is just the extent to which our total loss is higher than that benchmark. So if our total loss is 117 and the benchmark is 97, then our regret would be 20. Okay. Here's that exact same expression in math. The first term is the total loss incurred by our learning algorithm over the capital T time steps. The second term is just the minimum possible total loss achievable by a fixed weight vector in hindsight, given the adversary's choices. Okay. And the traditional goal, which we'll adopt here as well, is we would like regret to grow sublinearly in capital T. So if you think about sort of on a per time step basis, the per time step regret we're suffering on average should be going to 0 as we get more and more experience, as capital T gets bigger and bigger. Okay. And so that's a learning problem. L and chi are fixed up front. Adversary gets to pick the P's and the J, and our learning algorithm's playing around with the weights. But actually, if you think about it, it's not just a learning problem. It's really like a family of learning problems indexed by two seemingly different things. Okay, indexed on the one hand by a loss function L, squared loss, log loss, whatever. Indexed also by an aggregation method chi, okay, averaging, log pooling, whatever. For each choice of L and chi, you get an instantiation of this learning problem. And it's totally conceivable that maybe it's a solvable problem for some choices of L and chi, and it's not a solvable problem, meaning you can't get sublinear regret for other choices of L and chi. Okay, so we want to understand that better. We can think about this, we can study this problem either sort of at a general level or a specific level. So we can ask generally what properties of a loss function and aggregation method allow there to be online learning algorithms with sublinear regret, and we'll do that first. If there's time, we'll say a little bit about a specific case of a specific L and chi that we really care about, namely log loss and logarithmic pooling. Okay. So that is the learning problem that we're really going to focus on. And one more thing I want to say in this part of the talk, I want to suggest what property it seems, I want to suggest a property that's, seems in some sense necessary to have nice learning results, okay, which is a convexity property, okay? So we'd like the regret to be sublinear in T. Whether or not we can do that may depend on L and chi. And I claim it's very natural to focus on choices of loss functions and aggregation methods such that you get convexity in the weights. Okay, so again, remember there's 5 ingredients in this model. So let's fix all the four of them that are not the weights. So the loss function L, the aggregation method chi, those are chosen in advance. Let's think about fixed choices for the expert forecasts. Let's think about a fixed realized outcome J. The free remaining parameters are the expert weights. So we can talk about the loss as a function of the weights with everything else fixed. We would like to be convex, a convex function, okay, in the weight vector, no matter what the P's and no matter what the J is. Why do I say that? Why do I say convexity seems important? Well, just, look at the top, look at the definition of regret, and look at that second term. Look at that benchmark, best weight vector in hindsight, right? That's minimizing the sum of these capital L's. If the capital L's are guaranteed to be convex in the weights, that's just minimizing a convex function. That's something you can do efficiently using, for example, the ellipsoid method, or even, gradient descent, depending on what kinds of guarantees you want. If capital L is not convex, then even just something as simple as computing the benchmark typically is going to be an NP-hard problem. So if we want kind of online learning algorithms that are nice, either in the sense of polynomial time, or in the sense that they only use kind of basic machinery like first-order methods, it seems like you would really need these capital L's to be convex in the weights. You could imagine doing something more general and just looking, studying non-convex functions also, and ask about Oracle efficiency results, where I give you sort of a subroutine that I promised for you will solve this sort of problem on the right. We did not look at that. Okay, so we really wanted sort of genuinely efficient algorithms in the traditional sense. We wanted simple learning algorithms. And so for that, given those goals, it seemed like we had to focus on pairs of loss functions and aggregation methods that have this convexity property, so that the loss holding everything else fixed in the weights is a convex function. So the question I now want to ask is, so we wanted to ask the question, for which loss functions L and which aggregation methods chi can we have a good online learning algorithm, meaning sublinear regret? Now I'm saying let's also want an efficient one, and let's sort of identify that with convexity. And so now the question reduces to, for what traces of L and chi is this loss function convex in the weights? Okay. So let me pause here to see if there's any questions, right? So what have we done? I've told you just sort of the basic vocabulary, and I've specified fully the online learning problem that I care about. So if the online learning problem that I want to solve is not clear, you should definitely speak up. The other thing I've done is highlighted this convexity property it seems like we want. And the next part of the talk, we'll understand when it is that we get that convexity property.
Tim, have you thought about the pooling method itself changing, like giving the algorithm the ability to change chi?
We have, and in fact, Eric and I were just talking about that earlier this week. And we think, we need to verify this, but we think if just like, for example, you have a constant number of different sort of methods that you're looking at, and you know how to sort of do regret minimization for each of them, you should be able to also then kind of have a top level online learning algorithm that sort of figures out which of the K methods is the best one to use. That said, we haven't proved that. I mean, that's kind of a conjecture, but based on the proofs that we have so far, we suspect that would work out. Does that make sense?
Yes.
Hey, Tim, a follow-up question, which is,
Yep.
So if it's not a constant number that you're thinking about, but somehow this entire problem is maybe like the pooling is somehow parameterized, right? I know the weights are already a parameter, but if you think of like somehow the pooling method can be parameterized in some way, would convexity with respect to however that parameterizing happens also be sufficient?
Yeah, it's a good question, Jamie. You'd think maybe yes, I don't know. But let me answer it in a different way, which is exactly the point of this next part of the talk, is that given the loss function, there's really one aggregation method you should use. So in some sense, what I'm going to show you next is the choice of the loss function. I don't want to say it forces the aggregation method, but the whole point of the theory I'll describe in this third part is trying to justify, that really the loss function fixes the method you should be thinking about. So the only remaining task is then to understand what the weight should be.
Makes sense. Thanks.
Yeah. It's great questions. All right, great. So hopefully everybody's clear on sort of the online learning problem. We want to, for a fixed aggregation method, fixed loss function, we want to learn sort of the best weights. We want convexity in the loss with respect to the weights. When do we get that? Okay. Well, how do we get a feel for this question? Well, we can first look at it just in the cases that we know, right? I've given you two examples of aggregation methods, linear pooling and logarithmic pooling. I've given you two examples of proper loss functions, squared loss and log loss. That gives us four combinations. We can ask for each of those four. Is it the case that this loss is guaranteed to be a convex function of the weights? Okay. And so let's just fill in this matrix clockwise. I'm not going to go through the algebra, but none of these are particularly hard to show. maybe the simplest case, the first thing to try, squared loss and just averaging. You might expect that to be a particularly nice case, and indeed you do get convexity in the weights in that case. Interestingly, if you actually look at the way you can prove it for squared loss, the only thing you really need to fill in a yes in the upper left, all you need is that it's linear pooling plus a convex loss function. Okay, convexity is kind of all you need to push that argument through. Log loss is a convex function, then also when coupled with linear pooling will give you the convexity in capital L with respect to the weights. You might hope that the two logs sort of play nicely together, and indeed they do. So log loss combined with logarithmic pooling gives you convexity in the weights. At this point, maybe you think everything reasonable would give you convexity in the weights, but in fact, if you combine logarithmic pooling with the squared loss function, this term on the top of the slide is not generally convex in the weights. So this means there's something we have to understand, right? We actually have to understand under what conditions do we have convexity, under what assumptions about the loss function and the aggregation method. So what would be some, again, this is ridiculous interpolation from a tiny number of data points, but if we just wanted to look at the pattern of the yeses here, what could be going on? Maybe there's something special about the first row. We had all yeses there. Maybe there's something special about the second column. Or maybe there's something special about the diagonal, right? In the 2x2 matrix, there's a lot of hypotheses you can generate. Is there something special about the first row? Sort of, right? Like I mentioned that with linear pooling, all you need is for the loss function to be convex. Now, a loss function being proper does not imply that a loss function is convex. However, it is true that all of those sort of most popular, or almost all at least of the most popular proper loss functions are convex. So you would get a lot of yeses in this first row, okay? It turns out, if you play around with it, there's really nothing special about the second column, okay? The yes in the upper right is explained by the choice of linear pooling. It's not explained by the choice of log loss. If you added a bunch of rows, you get a lot of no's in that second column. But what's really interesting, and the point of this part of the talk, is actually there is really something special about the diagonal. What do I mean by that? I mean, there's basically going to be an infinite number of rows and an infinite number of columns. And so there's going to be a way to enumerate aggregation methods and enumerate proper loss functions so that you get yeses all along the diagonal. And that'll be the association between loss functions and aggregation methods that I mentioned. So, and this is now getting into the EC paper from last year. The choice of the loss function, right, that may reflect the application, right? We talked about, whether or not you're planning your kid's birthday party, you may have different ways of thinking about probabilities than when you're thinking about sort of military escalation. And so in particular, if you're really concerned about probabilities around 0, right, you might want to use sort of the log loss function, because that's the one that blows up as the probability gets close to 0. If you have more kind of uniform preferences in some sense over different probabilities, maybe the squared loss function makes more sense. So for us, when we talked about forecast aggregation, depending on properties of the application, all of the application specific stuff, we're going to assume that gets rolled up into the choice of which proper loss function you use. So stare at your application, decide how you feel about the relative importance of different probabilities, and then based on that, choose a proper loss function. Now, what would be really nice is if that's all the application specific work you had to do. Okay, once you had the loss function, the application, that same reasoning also told you which aggregation method chi you should be using. And that's exactly kind of the main results of the EC paper. So to each proper loss function capital L, we define a corresponding aggregation method chi sub L that satisfies a number of nice properties. This is obviously an informal statement, but this again is like maybe the sort of central part of the talk. So I will take time to tell you exactly what this correspondence look like and what these nice properties are. One of those nice properties will be the convexity property that we've been after from the learning problem. All right, so before I tell you the exact definition, what's the idea? The idea I think is pretty natural in a way, right? So what does an aggregation method do, right? It takes as input weights and forecasts, and it's supposed to output some kind of consensus or some kind of compromise between the forecasts. So intuitively, you want, it seems like you want some kind of center of mass, right, of the expert forecast, right? The expert forecasts are all kind of points in the simplex. You kind of want some center of mass in the middle of all of them, right? But as we said, that notion of center of mass should somehow depend on the choice of the loss function, right? Because we said the loss function is what encodes what's special about the application, and we have intuition that details of the application may influence how you want to do the aggregation. All right. So what's the simplest way we could carry that out? Well, we could say, let's go ahead and choose kind of the aggregate forecast, as something that minimizes the average distance, okay, to all of the expert forecasts. In that sense, it's sort of a compromise. Okay, I guess the experts have weights too. So let's say minimize weighted average distance, where the distance notion should be dependent on the loss function, okay? So your choice of loss function will determine the distance notion, but then given that distance notion, all of these chi-sub-Ls look exactly the same. They just minimize the weighted average distance to the reported forecast, where again, the weights are the given expert weights given to the aggregation method. Now, I'm gonna give you the exact formula here on the slide. My guess is at least a few people in this crowd kind of eat Bregman divergences for breakfast. So if you identify with that crowd, you'll look at this and you'll be like, dude, this is just like a suitable Bregman divergence. And you're right, okay, it is. It's the Bregman divergence of what's known as the savage representation of a proper loss function. We don't need any of that stuff, okay? So if you've never heard of that stuff, don't worry about it. I'm just gonna show you the formulas, which I think are pretty natural, just staring at them from first principles. All right, so I'm going to find this distance notion. I need to warn you, it's asymmetric. Okay, so the distance between from P to Q and from Q to P, they're going to be different. And so let's start with the second term. Okay, so the second term says the following. It says, suppose reality is that the realized outcome is chosen from some distribution P. Okay, again, that's not an assumption, in our model, but for the purposes of interpreting this term, imagine that there's some true distribution P governing the outcome. And then we imagine an accurate forecast, and we look at the expected loss that you would suffer, okay? Expected over the random choice of outcome from the assumed distribution P, okay? Expected loss of an accurate forecast when reality is P. Now, by virtue of capital L being proper, right, that's as small as this term can get. Remember, proper loss function means you minimize expected loss with an accurate forecast. So the first term is going to be expected loss when reality is P, but the forecast Q is inaccurate. And because capital L is proper, this will be an only bigger term than the second one, and this difference will be non-negative. So that's our distance notion. Okay, D sub L PQ, where L is the loss function. It's the extent to which your expected loss is higher with an inaccurate forecast of Q relative to an accurate forecast of P. That is how we measure sort of, how much, in some sense, how much of a compromise is needed to use Q instead of P. All right, so here's that exact same definition again. And now our association is going to be exactly what I promised. Okay, so we call this the QA pooling method, chi sub L, corresponding to the proper loss function L. QA here stands for quasi-arithmetic. And so given this distance notion up at the top, we just look, the method just outputs the consensus forecast P star, meaning the forecast that minimizes the weighted average distance to the PIs, where the weight in that weighted average are just the expert weights provided to the method. Okay, so in effect, right, you have all these experts that got the way to think about it is you have N experts, they all have wrong beliefs in some sense. And so you're trying to basically say which version of reality would make all of these experts feel kind of least bad about themselves, right? Would suffer kind of the least additional expected loss relative to if they had submitted accurate forecasts, okay? So that's the definition, all right? It actually seems reasonably natural, right? It's kind of a loss function dependent notion at the center of mass. I'm not saying it's the first thing you'd write down necessarily, but I hope it doesn't sound totally crazy. And indeed, as it turns out, has a lot of really nice mathematical properties. I'll detail those on the next slide. For now, just because I'm sure some of you are wondering, let me say that this is in fact well-defined, okay? Meaning that this argument, this minimization is attained, and it's attained uniquely. The reason that's true, this is really where we're using the assumption that the loss function is proper. That gives you the fact that the sum on the right-hand side is convex in its first argument, convex in what you're minimizing over P star. So that means there's going to be a unique minimizer for that right-hand side. And so chi sub L really is well-defined, whatever your proper loss function may be. All right, let me pause for questions real quick, because this is really, in some ways, it's a little bit technical, but in some ways, this is the, of technical statements, this is maybe the one I want you to remember out of the entire talk. So anything I can clarify at this point?
So these WIs earlier were the parameters that define P star, but now there's some kind of weights on the experts, and P star is not directly dependent on WIs. It's not like a linear combination.
That's correct. So in linear pooling is exactly where P star is the linear combination of the PIs. And we'll talk about when linear pooling is justified, but sometimes it's not. And if you're not doing linear pooling, then P star is a more complicated function of the PIs than just a linear combination. Okay, specifically, it's the solution to this minimization problem on the right-hand side.
So I guess what's confusing me is that where do these WIs come from? Like we were earlier learning them, right? So
yeah, so remember, so in the second part of the talk, we had the learning problem, and there the goal was to figure out the right weights. Then at the end of part 2, we said like, oh, well, as a prerequisite for having nice online learning algorithms, like polynomial time ones, it seems like we need this analytic property, which is convexity of capital L in W holding everything else fixed. So in this part of the talk, we're setting aside the learning problems, and we're just focusing on this analytic condition, asking when does it hold? Once we have a satisfactory answer to that question, we'll return to the learning problem and take advantage of the convexity that we just proved. Does that make sense?
Yeah, thanks.
Right.
Just a quick question. When you say proper, do you mean strictly proper for the uniqueness that you're talking about?
Yep. Yep, strictly proper. So the when reality is governed by P star should be the unique report. So any inaccurate forecast should be strictly penalized relative to an accurate one. Okay, great questions. All right. So hopefully everyone now understands this correspondence I talked about. To each proper loss function, we get a corresponding aggregation method where its aggregate forecast is defined as the solution to this convex minimization problem on the right-hand side of the blue equation. So it's well defined. Okay, great. That's fine. But like I'm sure it strikes you as like kind of abstract, right? So like a very natural initial sanity check would be like, okay, well, we have 2 proper loss functions we've been talking about, right? Squared loss and log loss. Why not just apply this definition and see what the corresponding QA pooling methods are? So first of all, you can say, well, suppose we take squared loss. This I think is not surprising. And then in fact, you do want to do averaging. Okay, you do want to do linear pooling if your loss function is squared loss. I think many of you would have guessed that point. A little bit more interesting. I mean, this is something you kind of hoped it would be true just based on like the syntactic similarity of these 2 phrases, log loss and log pooling. But it actually is true. Okay, so if you feed the log loss function into the QA, into this sort of correspondence, you get back the logarithmic pooling aggregation method. But more than either of these separately, I think what's really interesting here is, as far as we know, there was never, right? So it's definitely true that in aggregation, these are the 2 most commonly studied loss functions. These are the 2 most commonly studied aggregation methods. And what we're saying here is there's a natural pairing between the 2. And moreover, there's sort of a common sort of explanation for why each of those correspondences is what it is. And we're actually not aware of any other sort of previous explanation that sort of really, advocated this particular pairing, and certainly not one that kind of gave a common reasoning that these correspondences should simultaneously exist. All right. Anyways, so maybe this is just historical. When we saw this, we got excited. We were like, oh, wow, the 2 most famous loss functions go to the 2 most famous aggregation methods. Maybe we're onto something. And then, we asked ourselves, how would we convince the world that we're onto something, right? That anyone can make a definition, but like, why this one? Okay, what kind of evidence can we amass that we made the right definition or a good definition? So one thing we did is we justified it axiomatically. Okay, we said, well, look, we get all these aggregation methods as QA pools. Okay, so imagine ranging over all proper loss functions in the world, and then you get all corresponding QA pooling methods. So that gives you a big old set of sort of aggregation methods. I should have said this. There's a lot of proper loss functions in the world, right? So, I'm mentioning squared and log loss. It's a huge space. There's sort of a correspondence between proper loss functions and like convex functions. So there's kind of a lot of them. And so to each of those proper loss functions, you get an aggregation method. So that's this like really big set. And we show that this set of aggregation methods actually is also exactly the same set of aggregation methods that satisfies a particular list of 6 axioms that we all feel are quite natural. Okay? I want to emphasize these axioms do not speak about any loss functions. Okay? They're not sort of thinking about a case where you're doing loss minimization. The axioms are things like, as an operator, the aggregation method should be associative and commutative, right? So like it should be a function only of the unordered set of weight forecast pairs, not of like the specific names, for example. So those are the nature of the axioms. And what we show is that these axioms actually define exactly the same set that you would get ranging over all proper loss functions and looking at the corresponding QA pools. Okay. So that to us, was a mathematical way of saying that this family of aggregation methods is in some sense seems like a fundamental class. A lot of the axioms are kind of like really simple, like associativity and so on. One interesting one that we use is idempotence. And this may come up later if there's time, which just says if there's no disagreement among the expert forecasts, there's no reason to do anything else. If all your weather apps say 70% chance of rain, you're like, oh, I guess it's 70% chance of rain. Interestingly, there are models different than this one where you might actually want to break idempotence. Okay, but QA pooling always satisfies idempotence, which is appropriate when sort of different experts come to the same forecast for the same reasons in some sense. Okay, anyways, so that's an axiomatic justification of our definition. It defines sort of a set of methods that you could define in a totally different way. We also give a sort of optimization type justification saying that if you imagine a decision maker wanting to solve a certain min-max optimization problem, in fact, the right aggregation method to use, the optimal aggregation method to use for sort of worst case loss in some sense, would be the QA pool. Okay. I should say that this fourth one, at least our proof, needs assumptions a little bit beyond just that these are assumptions on the loss function, assumptions a little bit beyond just the loss function being proper, which is a little annoying. The good news is these minor conditions, they certainly hold for squared loss, log loss, almost any proper loss function you'd care to use. They do not hold for every single proper loss function. That said, we wouldn't be surprised if this statement isn't that true for every proper loss function. But our proof needs a slight extra technical condition. Under that exact same sort of mild technical condition, we get exactly the convexity property that we wanted. So this is what was important for our learning application. We said if we want to use like gradient descent or some other nice online learning algorithm, it seemed like holding all 4 ingredients fixed other than the weights. We wanted the loss to be convex in the weights. And whenever you look at the pairing between a proper loss function, subject to this like minor technical conditions, and the corresponding QA pooling method chi sub L, every such pairing automatically gives you the convexity you wanted. And that's what I meant by the diagonal of that matrix being all yeses. Okay, so the rows are indexed by proper loss functions with these minor extra technical conditions. The columns are indexed by the corresponding QA pooling methods. And this result says that the diagonal is made up of nothing but yeses. You have convexity all along the way. Okay. Even though this is a very important result for sort of in the context of this talk, I'm not gonna prove it. Proofs of convexity are usually either trivial or involve a lot of turning the crank algebra. This proof, it's actually in some ways a little bit in between, but it's a little bit more of the second one. So I'm going to spare you the turning the crank, and I'm just going to use this in what comes next. Okay. So the emphasis of our EC21 paper is really properties 3 and 4, but what's really relevant for the learning problem we're talking about here is this property 5. All right. So any questions about QA pooling before I now bring it back to talking about regret minimization? Okay, good. So that was the longest and sort of most technical part of the talk. So I just want to say a couple quicker things in my remaining time. So first, let's just, tie things together. Let's go back to the learning problem that we were interested in. Let's make use of this convexity property. As we'll see, convexity was the hard part. The rest is kind of taken care of by basically off-the-shelf technology. But I know it's been like 20 minutes, so let me just remind you what was the learning problem. Right, so we're thinking of L and chi as fixed up front. Now we know we're probably thinking of a loss function in the corresponding QA pool, chi sub L, but in any case, the general learning problem, you have L and chi fixed once and for all up front. Things take place over time steps. and each time step, the learning algorithm goes first, picks whatever expert weights it wants, presumably as a function of past performance of those experts. And then the adversary gets to pick everything else. Adversary can pick the forecast and can also pick the outcome. Once the adversaries picked the forecasts, along with the choice of the algorithm's weights, that forces the aggregate forecast P star. Then once you have that adversarially chosen outcome J, you know what your loss is. Just the loss function as a function of the aggregate forecast and the realized outcome. The goal, remember, is to minimize regret. So our benchmark is sort of the minimum total loss you could have achieved in hindsight with a fixed expert weight vector given the choices of the adversary. Regret is the extent to which our learning algorithm suffers more loss than that. And we would like that to grow sublinearly in the number of time steps. So the per time step regret should be little o of 1 as capital T goes to infinity. And as we discussed, we were sort of thinking probably it mattered which L and chi we were talking about. So we now get sort of a very, a fairly general positive result for the online learning of expert weights in this setup, okay? So specifically, really kind of a direct application of the convexity property that I left you with in the previous part of the talk. We get, as a consequence, just using online gradient descent, right? So as sort of first done by Zinkovich, whenever you have a loss function that's proper, okay, proper plus this sort of little bit of extra stuff, and for this slide, a loss function that is bounded, we'll get back to that, but for this slide, a loss function that is bounded, whenever you have such a loss function, and you use the corresponding QA pooling method, then in fact, you will be able to learn the right weights in the sense that online gradient descent will achieve sublinear, indeed square root of capital T regret, okay? And really the hard part was getting the convexity, okay? Once you have those of you who know a lot about online learning knows that convexity plays a really strong role in it, and there's tons of techniques to do online convex optimization well. Again, really just literally like version 1 of online gradient descent from Zinkovich already gives you this sort of root T regret bound for as long as you're using the right aggregation method chi sub L for this particular loss function capital L, okay? All right, good. So that's just putting parts 2 and 3 of the talk together. Part 2 was what we wanted. Part 3 was sort of the convexity properties of QA pools. And now here we're seeing, putting those together, we actually get what we want. Sort of. We get what we want for bounded loss functions, right? Which lots of loss functions are bounded, squared loss with plenty of others. But I have to concede, right? I've only been using 2 running examples of loss functions, and only one of the 2 satisfies boundedness, right? The log loss function is not bounded, and so this theorem actually doesn't apply. So that's a little frustrating, right? One of my 2 leading examples, I actually still don't have good online learning results for. So what's up with that? Let's drill down on that next. And what we'll see is that actually, for the log loss case and the corresponding QA pooling method, which is logarithmic pooling, we'll actually need to restrict the adversary a little bit. And furthermore, even under that adversary restriction, we're going to have to work a little harder, but in the end, we will be able to get our vanishing regret results happily. Okay. All right. Obviously, log loss is not bounded. So obviously, at least as stated, the theorem for bounded loss functions does not apply. But it gets worse, actually, which is that the theorem is simply false in our current model, with our current sort of notion of an adversary. Again, I'm talking here about log loss with the corresponding pooling method, which is logarithmic pooling. And sort of basically what goes really wrong, okay, the reason the theorem is false is because the adversary at each time step, right, remember, it gets to choose 2 things, right? It gets to choose the expert forecast, the PIs, and it also gets to choose the outcome J, the realized outcome at that time step, okay? And if you think about it, there's no coupling between those 2 things the adversary is choosing in our model thus far, right? The realized outcome J literally doesn't need to have any relationship whatsoever, okay, for the forecast reported by experts. All the forecasts could say 100% chance of rain, and the adversary can say, sorry, it didn't rain, okay? And so this coupled with the unboundedness of log loss, those 2 things work in tandem to show that that theorem on the previous slide is false. So basically, if an adversary, assigns, if you have 2 experts, one expert says something has basically 0 probability, the other expert is kind of like neutral 50-50. Turns out the log pool is going to assign the event also very low probability. And then the adversary can then just make that event happen, and boom, the log totally blows up. And the learning algorithm doesn't suffer infinite loss, but it suffers a really, really big amount of loss. So high level, the point to take away here is just that we've been working with a super powerful adversary that is not constrained to couple its realized outcome to its chosen forecast at all. We were able to get away with it with bounded loss functions. We're not able to get away with it with unbounded loss functions. Okay, we really have to pay the price for that strong adversary model in the log loss case. Was there a question? Okay. So, the obvious next step is to say, well, let's restrict the adversary and make it a little bit more reasonable, right? We still want the adversary to be able to do all kinds of crazy different things, but these are so-called experts, right? So it seems like we should be able to insist that the realized outcome has something to do with the forecasts of the experts, okay? So formally, we're going to be assuming that the experts are what's known as calibrated. Some of you, I think, will know exactly what that means. If you don't, that's totally fine. I'll define it for you now. So here's going to be our new adversary, which will be more restricted than our old one, but will still have lots of degrees of freedom. Let me describe it as sort of like a semi-random model, so kind of a hybrid of a worst case and an average case model. So an adversary in nature will collaborate to sort of produce kind of the input at a given time step of our learning problem. So the adversary, it's going to go first, and it's going to pick a joint distribution over everything that the adversary is in control of at a given time step, namely the n expert forecasts and the realized outcome j. So the adversary says, here's a joint distribution over n+1 tuples. Okay. Now, we're not going to let the adversary pick whatever joint distribution it wants. Again, we want sort of the outcome to have something to do with the forecasts. So this is the constraint we insist on. Okay. Every expert is calibrated. What does that mean? That means if sort of as an outside observer, okay, if the only thing you know is that a particular expert I, had some forecast P. Okay, so for example, right, that a particular outcome had 1% probability in their forecast, and that's the only thing you know, then the probability over the remaining randomness, okay, in the sample from this joint distribution, the probability of this outcome should be exactly what expert I forecast. It should be 1%. Okay, so if the only thing you know is that expert I thinks outcome J has a 1% probability, then if you see that over and over and over again, only 1 in 100 times should you be seeing a realized outcome of J. And that should be true for each of the experts and for each of the possible outcomes. Okay. So that's what I mean by every expert is calibrated. Conditioned just on their forecast, in expectation over the rest of the randomness, their forecast actually is accurate. In particular, like whenever an outcome is forecast to be very unlikely, it will in fact be realized very infrequently. All right, so this is what the adversary goes first. It picks whatever joint distribution it wants, subject to the calibration constraints. Nature is then the one who actually samples from this joint distribution, and it is that nature sample that gets passed on to the learning algorithm. Okay, the learning algorithm does not know, okay, that the adversary does not know the adversary's joint distribution. The algorithm doesn't even know per se that the joint distribution satisfies calibration. In the analysis of our learning algorithm, we will of course appeal to the fact, we will analyze it in the case where this joint distribution is calibrated. Okay. All right, so that's what I mean by hybrid model. Adversary picks a joint distribution subject to constraints. Nature samples from that joint distribution. That's what gets passed on to the learning algorithm. Now, if you haven't seen this before, you may be wondering, like, okay, like, have I just like totally painted the adversary into a corner where they basically can't do anything? Okay, they just have to do very benign things. But let me emphasize, this is a non-trivial constraint calibration. It'll flip things from not having positive results to having positive results. But the adversary, even subject to calibration, has tremendous flexibility remaining. Okay, in particular, it really has tremendous control over the correlation between different experts' forecasts. Maybe the easiest way to convince yourself there's a lot of flexibility is just to count the number of free variables and the number of constraints, okay? So the adversary is picking this joint distribution over these n+1 tuples, right? And really can specify an arbitrary sort of probability of each of those tuples. And so that's a number of free parameters that's scaling exponentially with the number of experts. Okay, so that's sort of how many free variables the adversary has to work with. Calibration imposes a number of constraints, linear constraints, that is merely linear in the number of in the number of experts. So you have a decent number of experts, you've got a huge dimensional space of possible joint distributions that the adversary can choose from, all the while satisfying the calibration requirement. Okay? So this is going to be our restricted notion of an adversary. Picks a joint distribution, has to satisfy calibration, but nothing else. Nature samples, gets passed to the learning algorithm, everything else is as before. And we show that actually calibration is sufficient to recover positive online learning results for log loss. And as usual, we're coupled with the corresponding QA pooling method, logarithmic pooling. In particular, we show this for the online gradient descent. It turns out does not work. Online mirror descent with the appropriate choice of regularizer does work in the sense that you get sublinear regret. Specifically, our bounds give square root of t log t regret. Okay. So the bad example for log loss and logarithmic pooling, this shows that really the only reason that example could exist was because of the unreasonable uncoupledness between the adversary's choice of outcome and the adversary's choice of expert forecasts. Not going to say much about the proof, obviously, at this late date. Obviously, we have to use the calibration hypothesis. Okay, otherwise this would be false. Basically, that means that whenever the logarithmic pool of the expert forecast assigns low probability to some outcome, that outcome is realized rarely. There's no way we're going to prove a good pointwise per time step regret bound. There may be the occasional time step where you have a massive, massive amount of regret. So we really need to analyze the expected regret in a much more careful way. There's kind of this quantitative tug of war between the forces of evil, which is that, the closer expert probabilities are to zero, the bigger the loss you might suffer is. And then the forces of good, which is that as probabilities get close to zero, the bad event is very unlikely to happen. And without doing the algebra, I don't know how you would know which of these forces wins. As it turns out, if you use a frankly pretty tricky, in my opinion, potential function argument that Eric came up with, you can prove that the forces of good win, and you do get sublinear regret. Okay, but this is not off the shelf. This one you really have to work for. Okay. All right, good. I just want to say 2 minutes on one topic, and then I'll be done. I alluded at some point, that when we're talking about the axiomatic characterization of QA pooling methods, that all of them satisfy idempotence, meaning that if all of the inputs to the aggregation method are exactly the same forecast, then the output of the aggregation method is also going to be that forecast. If all your weather apps say 70%, your aggregate prediction is also going to be 70%. Why would you ever not want to do this? Well, I claim you do want to do this if somehow there's a common reason why everybody's telling you the same number. If all the weather apps are using the same climate model, right, and getting to the same answer, there's no reason to kind of do anything different because it's sort of redundant. However, if different experts arrive at potentially the same forecast, but for different reasons, based on, for example, independent pieces of evidence, that actually motivates a technique known as extremization, okay, where you actually take the forecasts and you actually move it closer to either 0 or 1 as appropriate, okay? Let me give you an example. Imagine there's some coin and it has some bias, okay? And we have a prior, the bias chosen uniformly between 0 and 1. And your job is to guess the bias, minimize squared loss if you like. So knowing nothing other than the prior, you would say, oh, I guess my best guess is that the bias is 1/2. That would minimize my squared loss. On the other hand, think about an expert who gets to flip the coin once and sees heads. That expert's going to do a Bayesian update, and their new guess at the bias is going to be 2/3 if you do the simple arithmetic. Okay. But now imagine you're an aggregator, right? And 2 different experts both tell you a probability of that their guess is 2/3. And suppose that they each saw a different coin flip, each of which came up heads. Well, now as the aggregator, you in effect have seen 2 coin flips that have both gone up heads. So when you do your Bayesian update, you're going to get an even bigger number. Specifically, you're going to get 3/4. So in this simple Bayesian story, even though all of the forecasts are going to be 2/3, because the 2/3 are coming from independent sources, the optimal aggregate is higher than that. It's 3/4. It's in that sense, it's more extreme than just the common value of all the expert forecasts. Okay. And so that's just sort of a toy story about why this might come up, why it might be useful. It's actually been experimented with empirically, and it is actually quite useful in the sense that if you sort of look at data sets and you look at different aggregation methods and you sort of score them according to some loss function, often extremisation will give you sort of more accurate predictions than if you didn't use it. And so one question in one of our papers under submission is, can you have a robust theoretical justification for extremisation? Okay. And so the answer is yes. I'm basically running out of time, but let me just say a little bit about this. So if you think about it, I mentioned how this whole talk, we were making minimal informational assumptions, right? Like no priors, no nothing Bayesian at all. If you think about it, to make sense of extremisation, you kind of need a prior, right? Because you kind of need to know the forecast you're getting from experts. Are they higher than you expected or lower than you expected? Okay, in the former case, you want to push them even higher. In the latter case, you want to push them even lower. So you need to at least have some a priori sort of guess of what you think the probability of some event is going to be. Okay, but we're going to assume nothing other than that. Okay, so that's the minimal informational assumption that makes sense of extremisation. We continue to assume sort of calibrated experts in the same sense that we saw in the log loss case. There's also an interesting sort of informational substitutes type condition that we impose, okay, which is a sort of a topic for another talk. In any case, even with all three of these assumptions, the adversary has a tremendous amount of power. In particular, they can hide from you, they can make indistinguishable whether or not you're seeing 70% from everybody because they all have the same evidence, or whether you're seeing 70% from everybody because they all have independent evidence, okay? The adversary can hide that information from you. So any robustly good aggregation method has to kind of hedge between those two extremes. And what we prove is that extremisation is a great way to do exactly that kind of hedging. And the formal statement that we have, which shows that extremisation can be sort of provably necessary, is we show that in a sort of worst case approximation sense, worst case over the remaining flexibility of the adversary, extremisation is provably better, has provably better worst case performance than any prior free aggregation method you might conceivably use. For example, like the ones we were talking about at the beginning, log pooling and linear pooling. Okay, so with a little bit of extra information, you can make sense of extremisation. And our theoretical framework also tells you that you're provably more powerful by using that additional known prior information. And the way that you achieve that extra performance is through extremisation. All right, so I think I've wrapped up, pretty much out of time. I'll leave you with this final slide, just that lists a couple of open questions, which I'm happy to discuss in the Q&A, along with the 3 papers from which this work was drawn. So I'll stop there. Thanks very much.
I have a sort of stupid question / comment. If you're thinking about log loss and its unboundedness, one of the techniques that's useful in other contexts is to mix whatever probability distribution you were thinking about before with a small uniform distribution over all of your states. And I'm curious whether you've thought about that at all, or whether there are some like nice consequences of doing something like that.
Yeah, that's a great question. So as Jamie says, often with sort of, if you're implementing kind of using a logarithmic scoring rule in a prediction market or something like that, you basically don't allow people to report probability 0 because it sort of messes things up. You kind of force it, you sort of force a mixing in of the uniform distribution to keep things bounded away from 0. Eric, so I'll give an answer, and then Eric, feel free to chime in if there's more you want to add. In some sense, if you mix in any amount of the uniform distribution, it does turn log loss into a bounded loss function. And so that first theorem does in fact apply. The fine print there is that, the constants in the regret bound, I just emphasize the sort of dependence on capital T as is traditional, but there's a big O of root T. And in that big O is suppressing a constant that depends on how much the loss function can blow up. So basically, as a function of sort of how much of the uniform distribution you mix in, you'll be messing around with the constant factor in that first theorem. You might hope to have kind of a nicer interpolation between the bounded and the unbounded cases. And actually, Eric and I were just talking about that sort of earlier this week. We think that should be possible, but there's some work to do. It'd be nice to say that, suppose you mix in a little bit of a uniform, the first theorem, would give you a really bad constant, but some variant of the, some hybrid of the two theorems would give you something sort of really good. So we don't have a result like that, but the hope is that something like that would be true. Eric, was there anything you wanted to add to that?
Yeah, it's also the case that if you are coming from a perspective where you are particularly interested in pooling methods, and you find that logarithmic pooling pairs really well with the log loss function, then you might want to ask the specific question of how does logarithmic pooling do? Sort of the pure question where you're interested in assigning weights. And so from that perspective, I find this question to be theoretically motivated, even if you don't have the opportunity to mix in some sort of uniform thing.
So I had a question. Can you apply like calibrating to the expert forecasts before you put them into your aggregation to ensure that they're calibrated? And if you do that, does it kind of go through in a happy way?
Not sure I totally, Eric, do you?
Yeah, so my understanding of your question is something like, look at the prior history of those experts and then figure out what's the right function to apply in order for them to be calibrated.
Yeah, there was a talk yesterday and he alluded to this idea of calibrating where you can basically force experts to be calibrated and do at least as well as the expert predictions.
I guess that for the bad example where everything blows up if you have a fully adversarial model, that could happen in the very first time step where you have no history of how good the experts are. So it's possible that if you have some sort of reliable history of the experts, then indeed you can do pretty well. But at that point, I would say that it's almost like you are implicitly introducing a calibration assumption by sort of knowing exactly how the experts' forecasts should be manipulated and interpreted.
Any other questions?
Yes, we do.
Yeah, one question. Do you know if it's possible to get fast rates, say if you assume like some sort of X concavity or mixability assumption under which of these loss functions L you can get little root T rates for regret?
Yeah, that's a really good question. Like, Eric, correct me if I'm wrong here, but definitely, so we certainly haven't proven any upper bounds better than square root T. And if memory serves, we have lower bounds of square root T only for restricted families of algorithms. So it's even, I think, conceivable under our current set of assumptions, you could beat root T. Is that right, Eric?
That's right. In particular, we have a result that's something like, if you do OMD with a particular, with a fixed step size, then you cannot beat square root of T.
But in general, I mean, I think getting optimal rates, probably I should put that on the open question slide here. I mean, I think that is open, and that would be really interesting. It's conceivable you could beat the sort of root T barrier. Again, as you say, maybe under some extra assumptions, but maybe even not. So it'd be great to see work along those lines.
Thanks.
I have one question. Is there a way to compare the performance of different aggregators across the different loss functions?
Yeah, that's a good question. I mean, this is related to the question earlier about like, what if you wanted to also choose, what if you wanted your learning algorithm to also choose the aggregation method and not just the weights, right? Because what we've seen here is that like aggregation methods are kind of tied to loss functions. right? So it feels like, yeah, you'd have to decide on how to normalize, right? So I mean, any loss function you can apply in affine transformation. So you can take any pair of loss functions and kind of make them match, at appropriate 2 points or something like this. But it's still not clear to me that it's meaningful to compare different loss functions, in a general way like that. Do you have thoughts, Eric, on that?
Yeah, it's also not clear to me exactly. Like, I could imagine some sort of model where it makes sense to compare them, but like nothing obvious immediately jumps out.
It feels a little like apples versus oranges, but like Eric said, conceivably there's a way to address this problem, but we haven't figured out a good approach yet.
Hi. Yeah, my question is related to one that was like 2 questions ago, but if you take the special case of like the squared loss with like linear aggregation, like, so I'm coming from the world of like prediction with expert advice, right? Where we understand how to get constant regret. Like how much of the geometry still matches up, like at least in that special example, right? Where we know a lot about like mixable losses, and then here with linear aggregator and with squared loss, do you think like we have, in that example, do we have enough curvature to possibly, like, is all we have convexity, or do we have a little bit more, do you think? Because just knowing that you have a bit more might already suggest that you can get faster rates.
That's a good point. So you're even sort of suggesting the nature of the extra assumptions you might impose to get the fast rates, right? Where you kind of have some, where you basically you get second order information. Is that right? Or
so same information, but just like if the curvature of the loss carries forward when you use like the linear aggregator to like, the composed objects that you have. Yeah, so still like fully adversarial though.
Yeah, I don't have much. I don't have much to add. I mean, we did not, on the one hand, we didn't prove anything better than root T. On the other hand, I wouldn't say that was really our focus. And I do think, I would welcome work along those lines. I think that would definitely be interesting. Eric, do you have any thoughts on the plausibility of polylog or even constant or something like that?
What is the best you can do in just the normal learning with expert advice setting if your loss is squared loss? Is it square root of T, or can you do better?
You get constant. Yeah, you can get constant.
You can get constant. Okay. I don't know beyond convexity what other properties can be generally guaranteed for QA pooling.
That said, we didn't think about it, right? I mean, there might well be kind of some low-lying fruit there. It could be under, modest assumptions in the loss function. You get kind of, you get the extra analytic properties that would drive sort of these faster rates. That definitely seems plausible to me.
Yeah, so I don't mean to pile on the constant regret questions we've had, but in the log loss case, if you decouple the experts from the distribution, it's almost like the opposite of making the calibrated assumption. Like if they're uncalibrated, then you also get constant regret with linear pooling. So I'm curious about that. Like, if it feels like when you don't have them calibrated, it's like an easier problem because if you're competing against bad experts, that's only good for you. So I'm curious your thoughts on that.
So
yeah,
go ahead. The linear pooling part is really important there. Like, in a sense, we are making our lives harder for ourselves by choosing to do logarithmic pooling. This is motivated sort of by the fact that QA pooling is externally motivated. Basically the fact that the QA pool of let's say 50-50 and some extreme forecast is going to be extreme if you're using logarithmic pooling, means that if you don't have a calibration assumption, things can go really poorly for you. So while it is true that if you're using linear pooling, you can do quite well, like much better than square root of t. If you're using logarithmic pooling, you in fact can't get any positive result and need to rely on a calibration assumption.
Okay. Maybe.
Sorry, I just have a quick question, I hope. So you talked about like if people are making predictions based on common information, then you might want this idempotency. In polling, which is like presidential polling, like Nate Silver and 538, they actually, if they get the same estimated like prediction from a bunch of different pollsters, they actually bias towards 50-50 because there's like an assumption that there's actually correlated error, right? Like it's not that you're getting the same information and so it's good, it's that you're getting the same information, so they might all be using the same wrong information, so you might want to bias like back towards 50-50. It's like the opposite of extrematization. I'm just curious how you guys might think about that.
It's a good question.
Yeah. I think that we would say that the bias, right? So because we are assuming that the experts are calibrated, if the experts know that whatever procedure they are using will end up with a bias, they will account for that bias and drive back to 50-50 by themselves. And so like if the experts are using the same evidence then and reporting calibrated predictions, then the right thing for us to do is not extremize at all, but also not to push back toward the prior.
And certainly one interesting direction is to replace the calibration assumption with other restrictions, just other kind of types of modeling bias, sort of what, how the outcomes you expect to be related to the forecasts. So we really just sort of carried out the one because we thought it was the most sort of natural one to start with. But you could imagine other, whatever you want to call it, inductive biases or something about how the outcomes sort of connect to the forecast, and that would be interesting.
Maybe a little bit in relation to that. What happens if the opponents are epsilon calibrated? How does that carry over?
Yeah, I was thinking about this. Erica, I was actually thinking about this just this morning. I think it's fine for sufficiently small epsilon, right?
Yeah, for the results concerning extremization, I assume so. Regarding the logarithmic pooling results, since the regions around 0 and 1 are particularly sensitive, you might want some sort of like multiplicative or like an epsilon plus or minus epsilon to be added to like the log odds instead of the actual probability, so that an epsilon probability can't actually mean a 0 probability or vice versa.
Right. So for a suitable notion of approximately calibrated, right, it would, the log loss results would carry through, right?
Yeah, I think so.
Yeah.
Okay. Thank you so much, Tim and Eric. Clearly, you got us very excited with your talk. A lot of questions. A big round of applause again.
All right. Thanks, everybody. Very happy to participate. Wish I could be there. So have a good